This is a video about the corner right-hand rule, which is a rule that's used to find the direction of force that a magnetic field is putting on a moving particle or a current carrying wire. So these are the two corner right-hand rules. You can see that if you hold your right hand in exactly this shape, where each finger is perpendicular to the other finger, the thumb, the middle, and the pointer finger are all perpendicular to each other like this. These can accurately give you the relationship in the directions between the velocity of a positive charge, a magnetic field, and a force from the magnetic field on the particle, or the direction of current and the force from the magnetic field on the current carrying wire. So this shape is going to be really important. I'm going to give you an example of using it in just a minute, but while I'm doing that, just make sure that you can make it with your hand and maybe just look at your partner and see if they can also make the same shape and see if you agree. So just as a quick example of using the corner right-hand rule, we can imagine that we have a magnetic field pointing into the page specifically. These X's mean it's pointing into the page. And we have a positive charge moving this way. If you hold your hand up to the screen and have your pointer finger touch the screen, pointing directly into the screen, and keeping that same shape with your hand, rotate your thumb so that your thumb is pointing in the direction of the velocity of the positive charge, you're going to find that your middle finger is pointing up, like this, like straight up along the screen like that. So because the middle finger shows you the direction of the force, that is the direction of the force on this moving particle from the magnetic field. So that's how you use the corner right-hand rule. I'm going to give you a lot more examples of that in just a moment. Notice that when a charge enters the magnetic field, the field applies a constant force that is always perpendicular to the velocity of the charge. Thinking back to last year, a constant velocity and constant perpendicular force mean the charge will move in circular motion. If you don't remember that, I've left the circular motion video in the description here. This is something that's pretty important that you're going to have to remember. When a moving charge enters a magnetic field, it enters into circular motion because the force kind of follows it along at that 90-degree angle as it begins to turn until it leaves the field. So it will continue to move in circular motion until it leaves the field. The corner right-hand rule can also be used for a current carrying wire. So in this case, this is a wire that's carrying current to the right in a magnetic field that is pointing out of the page. So again, if you aim your thumb to the right and you point your pointer finger out of the page, you'll see that your middle finger is pointing down specifically. So that would be the direction of the force on this current carrying wire. And again, I'm going to do a few examples of using the right-hand rule on a current carrying wire on a piece of paper. Here we're looking at the force that a magnetic field applies on a single moving charge using the right-hand rule. So I'm going to form my hand into that right-hand rule symbol, so all three of my fingers are at 90-degree angles to each other, and just making sure that your pointer finger is pointing out and your middle finger is pointing sideways like this, not the other way around. So starting off here, I remember that my pointer finger points in the direction of the magnetic field. My thumb points in the direction of the velocity of a positive charge. That's going to be important in a little while. And my middle finger points in the direction of the force that's applied on the particle. So looking at this first one, I can see that the velocity is going to the right and the magnetic field is pointing straight down into the page. So I'm going to take my pointer finger and point it straight down into the page and take my thumb and point it to the right. And when I do that, I can see that my middle finger is pointing up specifically, like over this way up on the page. So that must be the direction of the force on that first charge. So the force is always going to be at a 90-degree angle to the velocity in some way or another. Sometimes it will point into or out of the page, but here my middle finger was pointing up, so it's going to point up like that. For the second problem, I'm going to do the same thing, but I remember that my thumb has to point in the direction of the velocity of a positive charge, and this is a negative charge. So we can do two things here. If I use my left hand, the rule will actually work for negative charges, but I find it easier to just say, okay, if the negative charge is going this way, the positive charge would be going in the opposite direction, so I'm just going to take my thumb and point it in the opposite direction of the negative charge. So I take my thumb and I'm going to point it up specifically, and I'm taking my pointer finger and pointing it in the direction of the magnetic field. And when I do that, I can see that my middle finger is pointing straight down into the page. So that must mean that the force from the magnetic field is pointing into the page. So using that vector symbol of an X for a vector going into the page, that is the direction of the force on this particle. For this one down here, you can see it's at an angle, but I can do the same thing. It's a positive charge, so I'll point my thumb in that direction, and I can see here that the magnetic field is coming out of the page, so I'm going to hold my pointer finger up out of the page, and when I do that, I can see that my middle finger is pointing in this direction, so that will be the direction of the force. Finally here, I'm going to use my right hand rule one more time. This is a negative charge, so I'll have to point my thumb down this way, and I can see that the field is pointing in this direction, so I'm going to take my pointer finger, point it in that direction. My thumb is pointing flat down like that, and I can see when I do that, that my middle finger is pointing out of the page. So that means that the force is also going to point out of the page specifically. So that's how you'd find the direction of force for a moving charge in a magnetic field. In this video, I'm going to go over 3 examples of getting other information from the right-hand rule other than just the direction of the force. So for all of these 3 problems, we know the direction of the force, and we're trying to figure out something else using the right-hand rule. In this first problem, we're trying to figure out the direction of the magnetic field. So I'm going to make my right-hand rule again and say that, okay, so I'm trying to figure out the direction of the magnetic field, and I can see that the velocity is pointing this way, and my force is pointing down like this. And I can see that my pointer finger is pointing straight up. So that must mean that the magnetic field is also pointing up. So the answer here is that the magnetic field is coming out of the page. For the second problem, I'm missing the velocity of this negative particle. So again, I'm going to use my right-hand rule and say that the magnetic field is pointing into the page and the force is pointing straight down. And so I would say that, oh, look, my thumb is pointing this way, so that would be the velocity. But my thumb represents the velocity of a positive particle. So if a positive particle would be moving this way, the negative particle would be moving this way. So that would be the velocity for that negative particle. Here I have the field and the velocity and the force, and I'm just missing the sign of the particle, whether it's positive or negative. So I'm going to use my right-hand rule to see which direction I would expect a positive charge to move, and if it doesn't move that way, it's a negative charge. So I'm pointing my pointer finger up, the force is down, and when I do that, I can see that my thumb is pointing in the opposite direction of the velocity. So that means that the positive charge, if this were a positive charge, it would be pointing this way. So because it's pointing in the opposite direction, it must be a negative charge. So that's how you can use the right-hand rule to find other missing information. Okay, let's use the right-hand rule to find the force on each of these current carrying wires. Starting at the top left, I can see that this current carrying wire is moving current in this direction, and the magnetic field itself, because these are X's, that means the magnetic field is pointing into the page. I'm going to start by forming my hand into that right-hand rule symbol. So I've got my thumb, middle finger, and pointer finger all at a 90-degree angle to each other. Just make sure you're not doing this or anything like that. So you have to make sure it stays in this symbol and that it is your right hand. So I find that it's usually easiest to start by pointing your pointer finger in the direction of the magnetic field, and here the magnetic field is pointing down into the page. So now that I have that, I'm going to keep my pointer finger pointing down, and I'm going to point my thumb in the direction of the current, and the current is going this way. And I can see when I do that, that my middle finger is pointing in this direction. So that must be the direction of force on the wire due to the magnetic field. So that would be the direction of the force in that first instance. We can now look at the top right and see what that looks like, and I can see here that I have a magnetic field pointing to the right this way, and I have this symbol for the current, which means that the current is coming out of the page. A dot or something similar to a dot means that the current is physically coming out of the page. So I'm going to have to use the right-hand rule again, so forming my hand back into that shape. I'm going to point my pointer finger in the direction of the magnetic field, and my thumb is going to point in the direction of the current, which is coming out of the page. And when I do that, I can see that my middle finger is pointing straight up. So that must be the direction of the force here. So because my middle finger was pointing straight up, that would be the direction of the force. Going down here, this one's at an angle, so it's going to be a little weird, but it won't be too bad. So I'm going to say that my pointer finger is pointing in this direction, and my thumb is pointing in this direction like this, because the current is going down like that. So if my pointer finger is pointing like this, and my thumb is pointing down like that, my middle finger is pointing out of the page. So that means that the force on this wire is coming out of the page. It's a dot vector, meaning it's coming out, rather than an X vector, meaning that it's going in. Finally, we have a current going into the page and a magnetic field pointing straight up. So magnetic field with my pointer finger, thumb pointing straight into the page like that, and I can see that my middle finger is pointing to the right. So that would be the direction of the force on that current carrying wire.